have one section left, but I won't be covering all of it today. 10.4 is about two root finding methods that are closely related. Newton's method, which is the subject of today, and then the Secant method, which I'll cover next Tuesday. And I'll read the last material, then review for final following Thursday. Okay, so we've seen two root finding methods so far. Bisection, that is very reliable and very slow, and then fixed point iteration, which under the right circumstances can be much faster. And at least there are some conditions under which it can be guaranteed that a solution is found. So now we're going to see another method that is generally faster still. So, and that's Newton's method, which you might have seen before. I know Newton's method is covered in calculus books when covering the applications of a derivative. But that just depends on whether the instructor covers it. So for some of you, but not all of you, it's maybe your first look at it. So the idea is that if you approximate your function f of x by some linear function, okay. All right, now we have two in the room. How do you make it? And here we have a line that's passing through some point x naught, y naught, where, and actually y naught would be f of x naught. So I'll just make that clear here. All right. So if we pick some linear function that passes through the graph of f at some point, then what we can do is a linear function is guaranteed, unless it's a horizontal line, is guaranteed to have a root. So what we can do is just set this equal to 0 and find the root, x star. The idea is, since this linear function is approximating f, then the exact root of this linear function will hopefully be an approximate root of f. So here's the formula right here, just rearranging. So in this case, y naught is f of x naught, and then m is the slope, but that's also the derivative. So here is a formula for an approximate root of a function based on a linear approximation. So the idea is, if your function f is a linear function, then this is the one and only root for whatever point x naught that you have. So we want to apply this idea to general f of x by using a linear approximation such as this. So, what can we do to, how can we approximate f by a linear function? There's more than one way to do it. For example, if you pick 2 points in the graph and connect the dots, then that is called a secant line for f of x corresponding to those 2 points. And we're actually going to use that idea next time when talking about the secant method. The approach that we use today is a linear function that approximates f near a single point x naught, where the slope of the line matches the slope of the graph. So the slope of a line is equal to the derivative of f at x naught. And of course, as you know, that would be the tangent line. So we've seen with regard to other problems, the general approach to designing numerical methods. You ask yourself, for which types of input is a problem most easily solved? In this case, what's the easiest function to find a root of? A linear function. Just as in the previous problems I covered, a numerical differentiation integration. Which functions are the easiest to integrate and differentiate? Polynomials. So we, so then once you answer that question, then the next question is, how do you then use that knowledge to handle the general case? Well, you approximate by one of those easy functions using one of these two approaches. So what we have here is for a given general function f of x, we make a tangent line approximation at some point x naught. So x naught would be some sort of initial guess at the root. So as done up here, you go ahead and find the x-intercept, and that's the same formula that I showed you right here. It's just that in the case of a linear function, this slope happens to be constant, but here it's whatever derivative is equal to at x naught. Hopefully it's non-zero. So now we have an approximate root. I'm sorry. This is the exact root of the tangent line. Therefore, it is an approximate root of f. Oh, missing a parenthesis there. Okay. So once we apply this formula, find the exact root of the tangent line. This is an approximate root of f that's labeled x1. So what we can do is keep going. We can take this approximation and apply the same formula to it to get x2 and so forth. So now we have this iteration. So the main step of the algorithm is whatever is our previous iterate, we substitute this formula to get the next iterate. And the idea is that hopefully the iterates will converge. And if the iteration is converging, that means that f of xk is going to 0. And sure enough, so this whole term will be 0. So the xk's will converge to some limit. So this is the main step of what is known as Newton's method, also known as the Newton-Raphson method. Apparently, poor Raphson has been forgotten. Actually, this is something I always like to check with regard to methods in general, especially when there's multiple names involved. Okay. Because sometimes it's surprising as to who actually is responsible for inventing the technique. Okay, what did Raphson have to do with it? As I'm looking at Wikipedia right now, and honestly, I'm not finding it. Okay, that's. So when Newton developed the method, he only applied it to polynomials, not explicitly connected to derivatives. He didn't give a general formula, but so the idea was used. And that was in the 1670s. Some years later, Raphson published a simplified description. Okay. All right. So he did more of an iteration, but it was Thomas Simpson who made it a general method that we're familiar with today, which is interesting because Thomas Simpson is best known for Simpson's rules that we saw from numerical integration. So he's made a big contribution here too. That was completely overlooked. His name is not in there at all. But actually, I think it should be. Newton-Raphson-Simpson's method. No one's going to remember that. It's like, oh, Newton did everything. One of my favorite historical facts about Newton is that this, of course, he's known as one of the inventors of calculus, and I have a number of people who are in Team Newton or Team Leibniz. But the idea about the inverse relationship between derivatives and integrals came from Isaac Barrow, who was one of Newton's teachers. Both teachers. Anyhow, back to Newton's method, or whoever you want to name it after. Okay. So all we're doing is each iterate, we're forming a tangent line approximation at that iterate, so it's the tangent at that point, find its exact intercept, and then use that as the next approximation, and we just keep repeatedly finding tangent lines in the hope of convergence. So let's find out, what kind of convergence can we expect? All right. So what's done here is I'm looking into the error after k plus 1 iterations and want to relate it to the error after k iterations. So how does the error change from one iteration to the next? So I start with xk plus 1 minus the exact root x star. And here I'm just replacing sk plus 1 by a formula from the iteration. And then, since I can just go ahead and subtract f of x star here, because that's 0. And then what I do is I perform a Taylor expansion. Now, with fixed point iteration, I did a similar convergence analysis, and I did Taylor expansion of g of x around x star. But I'm not doing it this time. I'm actually doing the Taylor expansion around xk. That makes things work out more nicely. So f of x star, which happens to be 0, is replaced with the Taylor expansion of f of x star around xk. And conveniently, these f of xk's cancel. And then what happens here is, here I have f prime of xk, here and here. So if I separate this part from the rest of a fraction, these will cancel, and then x star minus xk cancels with xk minus x star. In other words, everything here cancels, except for this. Just that term there. And that involves x star minus xk squared. In other words, we have quadratic convergence. So each error is proportional to the previous error squared. So that's significantly faster than fixed point iteration is in the general case. And here we have the asymptotic error constant. At least in the limit, as k goes to infinity, it would converge to f double prime at the root over 2 times f prime at the root. But what that means is, what if f prime is 0 at the root? What if we have a double root? That means this error analysis is invalid. And it can actually be shown that if x star is a double root, so f prime of x star is 0, because it no longer holds, convergence actually becomes linear in that case. And if it's just a double root, as in not a triple root or more, the asymptotic error constant becomes 1/2. Actually, I just realized I got ahead of myself because I think I actually showed this later in the notes. So, but, okay. Well, first, any questions about this convergence analysis and how we get quadratic convergence? Okay, so there's the asymptotic error constant. And here's an example for a specific function where clearly there's one root, x equals 1. That's a double root because it's x minus 1 squared. And so in this example, what happens is I want to do the same thing. I relate the new error to the previous error. So if I actually carry out Newton's method on this function, it turns out a lot of things simplify. It actually simplifies to this. So the new iterate minus 1 is equal to the old iterate minus 1 to the first power times this fraction. And since the root is 1, this converges to 1/2. So the new error is equal to roughly 1/2 times the old error. Whatever method has that property that's linear convergent, but the errors can be cut in half. We haven't seen many methods for root finding. Or anyone can suggest an answer in the chat. So anyone else just paying attention? Yes?
Could you repeat the question? I was
Okay.
zoned out.
What other root finding method it is bisection. Yeah, because the size of the interval we're searching is being cut down each time. And what I mentioned now about what a slow method bisection is. So Newton's method becomes very slow in this case because the error is only decreasing by at that rate. Now, simple might think, well, in this case, we might as well use bisection. Can anyone tell me why that is not possible? Why you cannot use bisection for this function? Think about what is needed to get bisection to work. What property of a function?
The intermediate value theorem.
Okay, what about it?
You have to have a positive and a negative.
There has to be a point whose derivative equals. There has to be a c between 2 points a and b such that f at some point equals c.
It's not quite saying it right. I'm sorry, James. I'm sorry, there's too much talking about it at once. James, what did you say? Or is it in the chat?
You have to have both positive and a negative value.
Right, and I don't know what you were getting at.
Okay, now I was stating the intermediate value theorem.
Oh, okay. Oh, yeah. Yeah, there has to be a sign change. This function is always non-negative. So it's not suitable for bisection. Okay. All right. So here, the constant, asymptotic error constant, turned out to be 1/2. What I was mentioning earlier was, that's not just for this function. Any function where there's a root of multiplicity 2, the error constant turns out to be 1/2. I believe, and I should be more careful about this because I did look it up some years ago. I believe that in general, if a root has multiplicity j, that the asymptotic error constant is 1/j factorial. I think because it comes from the Taylor series. But as soon as I said that, I was like, you know what? I'm not sure. It's either 1/j factorial, 1/j. It's buried in one of my books somewhere. But the constant depends on the multiplicity of the root. It's linear convergence regardless. Okay. Now here's my favorite application of Newton's method to a surprisingly simple function, a minus 1/x, where a is a positive constant. Now, I think, well, why do we need Newton's method for this? Because we can obviously set this equal to 0 and solve for x. Yes, but that's not the point. Because, of course, the solution is 1/a. So the root of this is a reciprocal of a. So we go ahead and take a derivative, 1/x squared, and then the formula for Newton's method gives us this. But then we can simplify this quite a bit, and we get this. So what's interesting about this process is this iteration, if it converges, produces the number 1/a. without performing any divisions. So it's a way to divide without dividing. And in fact, I believe it was in the 60s, there was a particular kind of IBM computer that used this iteration to perform division in hardware. Because modern computers have circuits to perform four basic operations: addition, subtraction, multiplication, division. This computer did not need a division circuit because it would use the other operations to carry out division. Now, that idea did not last. It's determined that it wasn't really the best option. Maybe at that time, division circuits weren't that great, and maybe they improved. I honestly don't know. That's my speculation. But it's considered a good enough idea to at least try carrying out this way. Now, let's see what happens. So as an example, we'll set a equal to 12, because that's my favorite number, as has come to this class before. For initial guess, we'll use 0.1, and the exact root is 0.08, so not far away from that. And I will show you what happens when I carry out this iteration with an initial guess of 0.1. So we get 0.08, 0.0832, and we see it converges pretty rapidly. So 5 iterations, and we're done. Now, let's do it again, but with an initial guess of 1 instead of 0.1. This did not go well. So here we have divergence. So we'd like to know what sort of initial guess should we pick. And it turns out what you can do, and I won't go through the entire proof, but if you ensure, assuming that A is positive, that the iterates stay positive, then the iteration will converge. And I'll show you why, what went wrong in this example using a graph. So here's a graph of this function. Now here, for example, I've chosen a equal 8, but same idea. So here we have a graph, here we have initial guess, and here's the exact solution at this case 0.125. And what happens is, if I choose this for initial guess and draw a tangent line, the x-intercept is way out here. So I end up on the wrong part of the graph. And I stay there. The iterates will just keep going off to negative infinity. So if you ensure that the x-intercept is positive, then you'll stay on the right portion of the graph, or the right and correct portion of the graph, and your iteration will converge. All right. Now, so what you can do is you can set this to be greater than 0 and solve for xk. And here's the condition. So each iterate needs to be positive and less than 2 over a. Now, I found that kind of unfortunate because 1 over a is the number you're looking for. So now you're saying you need to require your initial guess be less than twice the number you're trying to get. So that sounds really impractical. So that was my initial feeling when I realized this. But it turned out I was wrong. And I was not quite open-minded enough about this. So what got me thinking that I needed to re-examine this method, and this would be a good lesson for all of you, is some years ago, we had a thing where every week we'd hang out at McDonald's with some of our faculty, and there's one now retired computer science professor who expressed the sincere opinion that that this algorithm was the best way to perform division. I thought, what? What do you mean? You need the exact answer of your initial guess. he's thinking in terms of finding the solution within a floating point system. And that actually changes things. And I'll explain why. Because if we have some floating point representation of the number a that you're given, and so here's a mantissa, and we would know the exponent. That's the key. We may not know what 1 over a is, but because we know the magnitude of a, we know the magnitude of 1 over a also, by negating the exponent. So 1 over a has this floating point representation. Now, we don't know what this is, but we do know that it's within this interval. So what we can do is, if I choose 2 to the minus e for my initial guess, then then 2 over a turns out to be this, and because the upper bound has this floating point representation, and 2 over m is strictly greater than 1, less or equal to 2. So what that means is, if I forget about this, and I have my initial guess is therefore guaranteed to be strictly less than 2 over a. The key here is this is strictly greater than. And I tried this out. It actually works really well. Because we have an initial guess that's already in the ballpark. So, I was wrong. Okay. So, and yeah, it may not be the best method for forming division, but it was enough for the people years ago to give this a try. Okay. Questions about this? So as far as the benefits or drawbacks of Newton's method, so we've seen rapid convergence. It is the most rapidly convergent method we've seen so far for a general purpose method. And yet we saw a fixed point iteration generally converges linearly, can converge more rapidly in certain isolated cases. But Newton's method will converge quadratically most of the time. That's the huge benefit of it. But there are multiple drawbacks. You need a good initial guess. In certain cases, you may be able to get away with a faraway guess, like for instance, if the function is convex. You can do that, but for more ill-behaved function, if your initial guess is not close, the iterates could easily diverge. Another drawback is in terms of, believe it or not, efficiency. Even though Newton's method requires fewer iterations than other methods we've seen so far, each iteration is more expensive because you have to evaluate the derivative at each iteration. And for certain functions, that can be quite expensive. And that is why a good workaround is, instead of actually computing f prime, you can approximate the derivative using a difference quotient, like the numerical differentiation method that we've seen. Although it's not with equally spaced points because we don't have that. But if you just, so instead of, or equivalently, don't use a tangent line approximation. Use a secant line approximation, because as the iterates are converging to the root, the secant line is going to converge to a tangent line anyway. And that leads to the secant method. That's what I'll talk about on next Tuesday. What we'll see is that you do give up some convergence speed. It may take a little bit more in terms of number of iterations, but each iteration is a lot cheaper. So in the end, efficiency-wise, it turns out to be an advantage. Okay. All right. So good thing about Newton's method Alright, so systems of equations. If you have a system of nonlinear equations that has a vector value root, the idea behind Newton's method can be extended to that case, whereas a method like bisection cannot be. So in that case, you're computing, you have a function of several variables, and you're computing the Jacobian matrix of that function. So instead of dividing by f prime, you're multiplying by the inverse of the Jacobian matrix. So you're solving a system of linear equations at each step. All right. Now, one thing I've seen done regarding one of the other problems with Newton's method, like this case of having a multiple root, I want to mention a workaround for this. The idea is if f of x has a multiple root, the multiplicity greater than 1, then if you work with this function, which I'll call psi of x is equal to f of x over f prime of x, has a simple root. Right. And the reason why is, like for instance, suppose it's a double root. So you think of f of x as having factor x minus x star squared. Well, a double root of f is a single root of f prime, which would have a factor of x minus x star to the first power. Cancel that out. So then this quotient would then have a factor of just x minus x star to the first power. So apply Newton's method to psi of x instead. To obtain quadratic convergence. Can anyone tell me, if I were to plug this function, keeping in mind how it's defined, into Newton's method, can anyone think of a drawback to this approach, even though I would recover superior convergence? What additional disadvantage would this introduce? Anyone think what that might be? I'm sorry, I can't hear you.
It would fail if f prime goes to 0.
Well, yeah, that is a risk, but beyond that.
It's not new.
I believe that our formula is going to require us to use the quotient rule
It would.
and get quite a bit more complicated, yeah?
It would, but okay, now think through a process of applying quotient rule to this. So what?
We have to do the double prime.
Yes. Yeah. Double prime. Oops. Okay. Stupid thing. Double prime of x. So now you have two derivatives to evaluate at every iteration as part of the formula for psi prime. You cut down the number of iterations compared to something like this, but then those iterations get even more expensive. So it seems like there's no free lunch here, unfortunately. Okay. One other case that's worth mentioning I believe this is in one of the problems in a section that I did not assign. F is always increasing and concave, let's say, up. Okay. Or the other possibilities, like always decreasing and concave down. There are 4 combinations. Any of those. You can show, if you choose, depending on how you choose the initial guess, you can prove that the iteration is guaranteed to converge no matter how far away the initial guess is. All right. Okay, already questions about Newton's method? Or questions on homework? Or the final? Or anything else for that matter? Or why are we down break? I was honestly expecting no one to show up. But you two probably only here because of the modern.
Yeah.
Yeah, we had an exam.
Or did you have a test or something? Or?
Yeah, we had the third test for modern.
Oh, or you were about to have it? Or?
No, we finished earlier.
Oh, okay.
I think there's nothing else to do, so
Okay. Might as well show up here.
that's a good option.
Okay. Dr. Cole gave me cookies.
I'm sorry?
Dr. Cole gave me cookies.
No, he doesn't have modern. It's
No,
just-
I don't do what I like.
Just you. Oh, I said please. Okay. So at this point, you would have enough material to do, I believe, all but one of the problems on the practice final. I believe there's one problem on there involving Secant method. Yes, so if you haven't looked at it yet, there's a few problems where you're applying the various root finding methods, but also having to display a understanding of our convergence. Okay. Oh, actually, there is something I do need to announce about the final. I don't know if I'm going to do that today. All right, so what I will do is hold on. All right. Let's see. No later than on Tuesday, December 7th. All right. That's where I'll put it. And then on Thursday, December 9th. Also for campus. All right. So, so at a minimum, 53 hours. No questions about anything? Okay, fine, scram. Oh, I guess you can't. Yeah.